Assalamu alaikum. Welcome to the next lecture. In this lecture, we'll be discussing, we're continuing with the equipment earthing, and part of the equipment earthing is, as I told you, that it is done to safeguard the personals or humans, and uh, to safeguard, we need to have a particular value of resistance of the equipments which are connected to the ground. And before that, we need to first find out what are the safe currents and what is the range of the resistance of the human body. Based on these two values, we can design the resistance of the equipments, or we can say the grounding structure of any electrical system. So let's start with the safe currents through the human body and resistance of the human body. So generally 5 ampere 5 milliampere current which may flow through the human body is not considered to be dangerous. The current which is between 10 milliampere to 20 milliampere uh, is considered to be dangerous because victim loses muscular control. The resistance of the human body taken between two hands, that's the when we calculate resistance between two hands of human body, or between one hand and a leg, it ranges from 500 to 50 kilo ohms. 500 ohms to 50 kilo ohms. So for the calculation purposes, we may assume that the resistance of the human body is about 20 kilo ohm. So if the momentary contact with 230-volt line, you will see it is very fatal or very dangerous for a human life. It results in an amount of 11.5 milliamperes across a human body, assuming 20 kilo ohm resistance of the human body. And you may sometime have seen that if some person is touching this 230-volt line, he may not get any shock. It is because the body resistance, his body resistance may be very close to or even greater than this 50 kilo ohm. So in that case, he will not receive the shock because the current flowing through his body may be very less or even lesser than 5 milliamperes. So usually, Brunner states that the threshold of perception of electrical shock is about 1 milliampere. So as I have told you that 5 milliampere is not dangerous, but you can sense the electric shock, or you can perceive the electrical shock if the current flowing through your body is 1 milliampere. Now when with an increase in the AC current, the sensation of the tingling gives way to contraction of muscles. When this happens, contraction of muscle will take place. The muscular contraction increases as the current is increased, and finally the value of current is reached a value at which the person cannot release the grip on the current carrying conductor of the this should be the of the current carrying conductor. So there is a value of the current. If it reaches that value, that threshold value, beyond that a person will not be able to release the grip of the conductor which carries the conductor. So the maximum current at which the person is still capable of releasing the conductor, that means he has the muscular control still in his range. So by using the muscles directly simulated by the current, that current is known as let-go current, because this current after which it is able to uh, release the grip, that is known as let-go current. Based on the experiment conducted on males and females, it is generally expected that the safe let-go current could be taken approximately as 9 milliampere for the males and 6 milliampere for the females. So with these type of values, we need to design the earthing, particularly in case of substations or sometimes in case of homes where we have to use the earthing system. So with these things in our mind, we'll first discuss what is step potential and what is the touch potential. We'll start from the touch potential. The voltage that appears between the feet and the hand of a person which is in touch with the ground structure is known as touch potential. It is given by the equation, that is E touch is equal to 165 plus 0.25 rho 2 divided by the square root of Ts. This is the derivation of the touch potential or formula for the touch potential to calculate. Now the step potential, the voltage that appears between the 2 feet of a person which is in touch with the ground structure is known as touch potential. Sorry, it should be step potential. So it is given by the equation each step it is 165 plus rho 2 divided by square root of Ts volts. In this case, this rho 2 is the resistivity of the ground under the feet in ohm meter, and Ts is the duration of the current exposure in seconds. Now, why are these two potentials very important? The touch potential that appears between the feet and the hand of a person, it should be such that, because keeping in the mind the resistance of the human body, when you divide the resistance with the touch potential, the current that will flow through the human body should less than the Letgo current, or even lesser than that. So we need to design the ground structure in such a way so that touch potential will produce and step potential both will produce the current that is flowing through the human body which are less than that of the dangerous value. So in that case we have to either decrease this Ts or uh, to usually this Ts is not in our hand, it depends upon the relay structure. We have to decrease this rho 2, that is the resistivity of the ground structure. In case of substations, we make the ground mats or ground mesh in such a way so as to reduce the value of this rho 2, because in case of earth fault, when the fault occurs involving the earth, the fault current will flow through the earth, that means the ground structure, and when the current flows through the ground structure, that current multiplied the resistance of the ground structure will give some potential, and when then that potential appears across our legs or between our hand and the feet, it will appear some voltage, and that we have just discussed, that is known as touch potential and step potential. So we need to design this rho 2 in such a way, that resistivity of the ground structure in such a way so that the touch potential and step potential are very small, which will not uh, pose any danger to a human body. So based on these observations, a general rule is that the lower the value of resistance, better it is, even then the following value of the earth resistance values are given the satisfactory result. We just want that this resistance should be as low as possible, but the maximum values may be there. That means for large power stations, the earth resistance should be as high only as up to 0.5 ohms, and for major power station, that is medium power station, it should be 1 ohm. Small substation, it should be 2 ohm, and in all other cases it should be a maximum of 5 ohms. So in large power stations, the value of the resistance is smaller because the current value is higher, and in that case that current multiplied this resistance gives some voltage that will be still higher. That's why it is resistance should be lower. This is all about earth potential, equipment earthing, uh, touch potential, safe currents of this that is flowing through the human body, and based on that we designed this you can say resistance of the grounding structure in case of substations. So it is a part of a design perspective. We did it on the design perspective. So now come to the neutral system, or you can say grounded system. But before going to the grounded system, or this grounding of the power system, we'll first see what are the disadvantages and what are the problems that are associated with the isolated neutral or ungrounded system. This is a schematic diagram of an ungrounded system where the neutral of the system is not connected to the ground or earth. So under normal conditions, under balanced conditions, you will see this is voltage VA, VB and VC are balanced and they are displaced from each other by 120 degrees, and currents, and they are also having some phase angle with respect to the respective voltage, and they all the three currents which are flowing through the phases, they are also balanced and they are displaced from each other by 120 degrees. So this is the isolated neutral, and in case of the neutral grounded system, they will remain the same. There will not be any we can say the phasor diagram and the currents and voltages will not pose any difference and will not have any difference under balanced conditions and under normal conditions. But in case of under abnormal conditions, let us say we have a line to ground fault on phase C, and line to ground fault occurs on phase C. That means this phase C is at ground potential, or since this ground is not were not consider it to be the zero, that means ground potential will now raise to potential of the C. That means this or we can see neutral has shifted from this point to point C. You can see from here. Then the voltage of A, which was with respect to this neutral, that was this vector, it will be now, because this neutral has shifted to point C, this voltage A with respect to ground, that means the ground is now at potential C, will be VAC. That is shown over here. This is the VA. It becomes now VAC. Similarly, for B with respect to ground, the ground is now at potential C because we are assuming a line to ground fault at phase C. So this voltage B will rise to VBC and its phasor will be like this in this direction. That is shown over here. Now the current, that is the capacitive current, we are assuming unloaded system. The capacitive current in case of phase A will be with respect to VAC, that is with respect to this vector. You can see with respect to this vector, the capacitive current, because this we are assuming the current between this phase A and ground, and we have already seen that there will be a capacitance between phase phases and ground. This is the fictitious capacitor. One conductor will act as one electrode or one plate of the capacitor, and earth will act as another electrode of the capacitor, and the air in between them will act as a medium or dielectric. So in that case, capacitive current in case phase C will be phase A will be leading to this VAC by 90 degree. That will be this current will be flowing through this, that is root 3 IC, and the current flowing through this root 3 IC will be leading 90 degree to VBC, that is this current. The total current will be the summation of this current 3 times IC, because the total current will flow through this winding back to this third winding, which is the faulty winding. So IC is actually the current which is flowing in a normal case, that is this current. This is again the you can say diagram for in case of when we have a fault, but you will see that this is VA, this is ICA, actually IA. You can see this is IA over here. In this case, IA is leading to this VA by 90 degrees, and this IA will be equal to actually IC, that IC will be equal to VA omega C, where VA is the phase voltage of this A. But in this case, you will see that since this is root 3 IC, because the voltage across this capacitor will be now the line voltage, that is the current will also be multiplied by root 3, and the total current, that is the fault current, we can see in this case, that is 3 times IC. It is because of the summation of this current and this current that will flow through this and then back to this through this winding of the generator. So this is how this can be done. There are two things that you need to understand from this discussion. One is that the disadvantage of this isolated neutral is that the phase voltage has uh, increased to the line values. The other phase voltage which are not involved in the fault. So the faulty line has definitely zero voltage with respect to ground, but other voltages will rise to the line value. That is the disadvantage of this. One more thing that we need to understand, that this current 3 times IC, even if it is a fault current, its value is very small, and in case of protective relaying, it is not usually detected by the relay, because load current will be still greater than this current, is 3 times IC, and identifying this with respect to or we can say differentiating this current from the load current will be difficult for us, and it will not be we can say detected. In case of single line to ground fault, in case of isolated neutral system, will not be detected, and in case of ideal case, you will see this 3 times IC will also be equal to 0, because if you see that it is as if practically there is nothing between this and this, there is an open circuit between phase A and ground, there will be no current. But in case of when a line to line, if this single line to ground fault occurs first, and then after this other line is involved in the fault, there will be a line-to-line fault and triple line fault. So here the disadvantage is that we're not able, the line values, the phase values will increase to the line voltages, and there is the protection is not guaranteed. This single line to ground fault is not detected. And there may be another thing, the presence of the inductance and capacitance of the system, that is inductance is this and capacitance is this, may lead to what is known as the arcing grounds. So, and the voltage of the system may rise to dangerously high value. We'll see this in this case. So these voltage can be eliminated by connecting an inductance of suitable value between the neutral and ground. We'll see this also. If the value of the inductive reactance is such that the fault current IL, that is this current, balance exactly the charging current, then the grounding is known as resonant grounding or ground fault neutralizer or Peterson coil. We'll discuss it in detail in the coming slides. Now we'll first discuss the arcing ground. This is one of the disadvantages of the this isolated neutral, apart from this increase in the line voltages, increase in the phase voltage to line voltages, and non-detection of the earth faults. So under balanced conditions, this will be our phasor diagrams. The voltage will be you can say displaced from each other 120 degrees, and the sum of three currents, that is the capacitive currents, will be equal to 0. Now when a single line to ground fault occurs in one of the phases, let us say it is phase C, the voltage across the shunt capacitor of the three phase reduced to 0. You will see the voltage across this will reduce to 0, whereas those of the healthy phase it becomes line to line voltage. Now they are displayed by 60 degrees rather than 120 degrees. You can see from here, this is VA, this is VB, they are displayed by 60 degrees. Earlier it was 120 degrees because they will now become line voltages. Now this is very important, and this actually is the explanation of the arcing ground. The net charging current now is a 3 times the phase current under balanced conditions. So this charging current will be now 3 times that of the charging current which was under the balanced conditions. Now this 3 times will be in case of single line to ground fault. So these currents will flow through the fault and through the winding of the alternator, that is from here. This current will flow through this and then like this, then like this, and then to the winding of the alternator. The magnitude of this current is often sufficient, that is in excess of 4 amperes, maybe 5, 6 to 10 amperes, to sustain an arc. This arc will be sustained between the phases, healthy phases, and the faulty phase, or we can say healthy phase and ground. It may result in the ionization of the air. That is what arc is. That's what is meant by an arc. And therefore, when arcing ground, such type of condition will be denoted as arcing ground because it will produce an arc between the healthy phase and the ground because of this charging current. This could be due to the flashover of the supporting insulator. This arc is sustained because of the flashover of the insulator. Here this flashover acts as a switch. It is because, please try to understand this line, since this arc, when the arc produces, it results in the flow of the current. When current produced, that current, AC current, will pass through the zero as well. When this arc passes through the zero, it extinguishes because there will be no current, there will be no ionization of the this air. It will reduce to zero value. The capacitors in phase and B are charged to line values, and with this the capacitors will be charged to the line values. Now the voltage across the line and the ground points of the post insulator will be the superposition of the capacitor voltage and the generator voltage, and this voltage may be good enough to cause a flashover which is equivalent to reset the circuit breaker. Now in this case, since this acts as a switch, this arc, now it has extinguished. There is an open circuit. Now there is a voltage across the capacitor and there is a voltage across the source, that is the across the this we can say generator. These two voltage add up and they will appear across this. We can say this acts as a switch or circuit breaker. That is the where this arc has extinguished. Now this voltage is actually this very high, and it will restrike again, and it will cause the arc to produce again. And this makes this air ionized, and the arc will restrike again. Now, because of the presence of the inductance of the generator winding and the capacitance, they will form the oscillatory circuit, or we can say resonating circuit. And these oscillations, when the oscillations occur, they may build up a still higher voltage, 5 to 6 times the normal value, and the arc may reignite, causing further transient disturbances. Arc will reignite again, and it will result in the further disturbances, which may finally lead to the complete rupture of the post insulator, and it results in the rupture of the post insulator. So this is very important in this case. This arcing ground may result in the high voltages. It results in the continuous, or we can say intermittent arcing between the healthy phase and the ground, and finally it may result in the rupture of the post insulator. This is one of the disadvantages. The last one is that the system cannot provide adequate protection against the earth fault. As I have told you, it is because the capacitive fault current is small in magnitude and cannot operate the protective devices. Because these currents cannot be detected successfully, the current should be very high so as to detect the earth fault. And ideally, you will see these currents we actually neglect with respect to load as well. Since I told you it is 4 ampere, in case of load, it may be of the order of hundreds of amperes. Now coming to the neutral grounding, we have usually four types of neutral grounding: solid or effective grounding, resistance grounding, reactance grounding, Peterson coil or resonant or arc suspension coil grounding. As I have told you, this will be the case when we totally nullify this capacitive charge and current. Now starting with the solidly or effective ground, what does this mean? When the neutral of the three-phase system, for example three-phase generator or three-phase transformer, is directly connected to earth through a wire or soil through a wire of negligible resistance and reactance, it is called solid grounding or effective grounding. So this is how when a neutral is connected directly to the ground through a wire whose resistance or reactance is very negligible or close to zero. Now what are the advantages of this? The neutral is effectively held at the earth potential. In the previous case, neutral was when fault occurs, when neutral comes out to the potential of the phase C. But in this case, it will be held at the neutral potential. When the earth fault occurs, so any phase, the resultant capacitive current is in phase opposition to the fault current. You can see that here. Earlier, this is IC. VA and VB will remain at its own voltages because now this neutral is not changed. Neutral voltage will remain at zero voltage. Now this is current IC which is flowing through the phase A. This is current IC which is flowing through the phase B. This is the total current. You will see when the two currents are added, which are or two phasors are added which are displaced by 120 degrees, the magnitude will remain the same. That's why it has remained here IC. Now when the current flowing, you can see from here, this will be at zero potential or ground potential, and the current flows through this. This is the fault current. That fault current which will be in phase opposition to this fault current, that is this IC, and it will try to nullify it based on its magnitude. In this case, the IF and IC will not be same, but it is in phase opposition. So the two currents cancel each other. There is not a sufficient current which may result in arcing ground or over voltage, and over voltage condition is eliminated. When there is a fault on the other phase of the phase of the other voltage becomes zero. The faulty phase voltage becomes zero. However, the phase to earth voltages of the remaining two healthy phases remain at the normal phase values because the potential of the neutral is fixed at our potential. And one more thing, that since this is connected to the earth, and when this phase C is touching to the earth, there is a huge current flowing through it, which is even greater than the load current. And in that case, this earth fault is quite easily, earth fault current is detected by the protective relays, and this can be disconnected from the system. When there is an earth fault, and then if a large fault current flows between the fault point and the ground system, this permits an easy operation of earth fault relay, and we can say detection and isolation of the system. This faulty part of the system can be isolated. Now this is applicable usually where the circuit impedance is sufficiently large so it's kept the earth field current within the safe limits. The system of grounding is used for a voltage up to 33 kV with a total power capacity not exceeding 5000 kV or 5 MVA. Now the second one is the resistance grounding. So you can see from the name itself, when the neutral point of the three-phase system is connected to earth through a resistance, it is known as resistance grounding, and it is connected like this. It's very simple. So why do we do the resistance grounding? In order to limit the magnitude of the earth fault current. So It's a common practice to connect the neutral of the three-phase system to the earth through a resistor. The value of R should be neither very low. If it is very low, it becomes close to the uh, we can say solidly grounded system, or it should not be very high. It becomes close to the isolated neutral system, because high value of resistance means it is only maybe considered to be open circuit. Now you can see from here, when the fault occurs in case of C, the fault current will flow through this, and in the fault path we have an impedance of L and R, and you can see that this is VA, this is VB, and this is IF. So IF will be lagging to the voltage of neutral voltage, that is VCN, by an angle of phi depending upon the value of L and C. So IF will have a component IF sine theta, which may be directly in a phase opposition to this fault current IC, and in this case a portion of this IC will nullify this fault current, and in this case arcing ground and over voltage will be eliminated. And in case of solidly grounded system, it has a disadvantage that the ground current, or we can say the neutral current, is very high, and it results in the interference with the communication circuits. But in case of resistance grounding, interference, because the current is less, there will be less communication circuit interference. Also, it improves the stability of the system, so it is used uh, in the grounding the neutral of synchronous generator. So usually this resistance is used in grounding the neutral of the synchronous generator. So this is actually there. When the earth fault occurs on the phase, the resultant capacitive current IC is in phase opposition to the inductive component of the fault current IF. The two currents completely cancel. It is not completely cancel each other, but they somehow complete. We can say are phase opposition to each other, and the arcing grounds are eliminated, which result in the decrease in the over voltages. So this is used in a system with the operating voltages between 2.2 kV to 33 kV, and the power capacity is more than 5,000 or 5 MVA. The disadvantage of this case is that in case of the fault, there is a power loss, definite power loss in a resistance, that is I square R loss. So to eliminate that power loss, we may go for the reactance grounding. In this case, the neutral is connected to the ground through a reactance. And there is a particular relation for a reactance grounding system if the x0 by x1 is greater than this 3, and for solidly grounded system x0 by x1 is less than 3. This x0 is known as zero sequence reactance, and it is, we can say, directly reflection of the reactance of the neutral. So x1 is the positive sequence reactance, and we will discuss them in detail in the power system second course. For the time being, we can say that this x0 is the reactance of the, we can say, neutral. So when x0 by x1 is greater than 3, that means that this reactance has a good value, that means it's a reactance grounding. When x0 by x1 is less than 3, that means this x0 has very small value. In that case, we can consider this to be solidly grounded system. This method of grounding may be used for grounding the neutral of the synchronous motor. In resistance neutral, it was used for neutral of the synchronous generator, but reactance grounding is usually used in case of neutral of the synchronous motor and capacitors, and also for circuit having large charging currents, because in that case it is used to nullify those charging currents, capacitive charging currents. This is reactance grounding, and advantages are same as that of the resistance ground. Apart from that, there is no loss when a current flows through this reactance. The last one is the Peterson coil or resonant arc suspension coil grounding. It is, we can say, similar to the reactance grounding, but its value is the value of the inductance is variable, and that varies. We can see what we do with the variable, this reactance of this. We have seen the capacitive currents are responsible for producing the arcing grounds. These capacitive currents flow because capacitance exists between each line and the earth. If inductance L of appropriate value is connected in parallel with the capacitance of the fault current IF flowing through L will be in phase opposition to the capacitive current IC, as we have seen already in case of this inductive circuits. If L is adjusted so that IL is equal to IC, then resultant current of the fault will be 0. In the previous case, it was not exactly 0, but this IC has decreased because of the presence of IL or part of this I. So in this case, the Peterson coil or resonant coil, it has been made equal to 0. That is why this condition is known as resonant grounding. When the value of L of arc suspension coil is such that the default current I have exactly balanced the capacitive current, it is called resonant grounding. So in this case, this arc suspension coil, which is also known as Peterson coil, is an iron core coil connected between neutral and earth, as shown in this. You can see from here. This is similar to an inductance, or you can say reactance grounding. Only thing, it has a tappings over here. So the tappings are changed to exactly balance this current and this current. You can see they are balanced each other, and the net current that flow through this will be equal to 0, and there will be no arcing and there will be no over voltages. So by adjusting the tapings on the coil can be tuned with the capacitance of the system, that is resonant grounding can be achieved. Let V phase be the line to ground voltage of the system. The voltage of the healthy phase during the healthy fault will be √3 V phase. If C is the capacitance to ground of each phase, then the charging current will be 3 times V phase omega C. That we have already seen, that it will be equal to 3 times IC. So in terms of phase voltage and omega C, it will be like this. And the current flowing through the inductance of the neutral, that's Peterson coil, will be V phase divided by omega L. So under balance conditions, this current should be equal to this current. That means V phase by omega L should be equal to 3 times V phase omega C. So in this case, L will be equal to 1 by 3 times omega square C. The use of the resonant grounding will reduce the line interruption due to transient line to ground faults, which will not be possible with other forms of the grounding, because in this case, the two currents exactly cancel each other. Also, the tendency of the single phase to ground fault developing into the 2 or 3 phase will be decreased. So this is the advantage of this. Let us try to do numerical on the same that's Peterson coil. We have 132 kV 3-phase 50 Hz transmission line, 192 km long. It consists of the conductor whose effective diameter is 20 mm, arranged in the vertical plane of 4 meter spacing and regularly transposed. So find the inductance and kV rating of the arc suspension coil in the system. The capacitance of the phase is given by, as we know, that 2 pi epsilon ln of d by r. This is 2 pi epsilon ln of d by r, where d is d equivalent. Since they are on the vertical plane, d equivalent will be equal to cube root of 4 into 4 into 8, and its radius is 10 mm, that is 10 into 10 to the minus 3. Calculating this and multiply the total length of the line, it will be equal to 1.72 microfarad. So we know that L is equal to 1 by 3 times omega square C, so it comes out to be 1.97 Henry. So MV rating will be equal to V square by 3 omega L. Actually, this should be V phase square. When you use the line, the 3 comes over here. It comes out to be 9.389 MV per coil. Now we have one more thing, that is earthing transformers. This is used when the neutral point is required, which otherwise is not available. For example, in delta connection or bus bar points, because their neutral point is not available. In that case, a zigzag transformer is used. These transformers do not have the secondary winding. They have only one winding. Each limb of the transformer has two identical windings wound differentially, such that under normal conditions the total flux in each limb is negligibly small, and therefore the transformer draws very little magnetizing current. I will show you just a minute. The grounding transformer are short time rating, usually 10 seconds to 1 minute. Therefore, the size of such transformer is small as compared to the power transformer, the same rating, because power transformers are used continuously for the full load. This is the grounding transformer. This is the usual 3-phase system, and you can see we have only one line. Only you can see what do I have? Two identical windings found differentially. Wait a minute. We have two identical windings like this and this, this and this. You can see the current flowing through the identical windings is opposite, so net flux will cancel each other, and there, so that there we can say their size will be very small. And this is the neutral point of the system. This connection over here is the neutral point of the system, and when such cases occur, we can use this as a neutral, because for single phase system, or why the neutral is, if we don't have a zigzag transformer, we can use a star delta transformer over here to take the neutral of the system, or to make the neutral of the system available. Thank you. I'll stop over here.